So once again, what makes it harder when we want to cluster? Well, first of all, if you want to cluster, if we are in the unsupervised setting, we don't know anything about the data. We don't know what kind of patterns are in there. Now, with high-dimensional data, we have another challenge, which is relevant or irrelevant features for the patterns. So we don't know about the patterns, and we don't even know about which kind of features are relevant for those unknown patterns. So that makes it even worse. Yeah, let's just reconsider all the stuff and all those challenges here in a kind of three-dimensional example, which is coming up here. So first of all, what is the effect of clustering on clustering of irrelevant or redundant attributes or whatever? Well, first of all, we know that traditional distance functions, of course, give equal weights to all dimensions, to all attributes. That means these distance functions, these distance measures, and also, of course, the similarity measures that we know or that we get to know so far, and that is most of the stuff which is out there. They just don't distinguish between relevant or irrelevant attributes. They just think that everything is relevant, so everything gets equal weight. Yeah. However, of course, not all dimensions are of equal importance, depending on which kind of patterns we want to find, and depending, of course, on the relevancy of the corresponding features. So adding irrelevant features, dimensions, of course, has to somehow ruin any kind of clustering based on distance functions, because if all dimensions are equally weighted and we have a lot of irrelevant attributes, then we have all the nice stuff of the curve of dimensionality we talked about a couple of weeks before. Yeah, because if you recall, all of these bad things happen if we assume that we have a lot of irrelevant attributes. And if we do so and give equal weight to all features, we don't distinguish between relevant and irrelevant attributes, then we have the curse. Yeah? And of course, that is not what we want. Yeah, and here is an example, which is the same example as before, where we have also not only these relevant or irrelevant attributes, but we have different attributes to be relevant for different clusters. Yeah, so that is the baby-shaped game, so to say, and that is already happening here in this two-dimensional or three-dimensional example. So this is the data set here. Color-coded are 4 different clusters: a green one, a red one, a purple one, and a blue one. And well, in the three-dimensional case, you don't see too much of it because they are highly, well, not perfectly overlapping, but they are quite overlapping actually. Yeah? And now, depending on which kind of two-dimensional projection, I mean, this is a three-dimensional data set, so we can take this projection here to look at the data set on from one view, so to say. We could take this two-dimensional projection, or we can take this two-dimensional projection here. Yeah, and we can look at 3 different perspectives, 3 different two-dimensional perspectives on this data set. And if we do so, well, if we take the wrong one, we see that we cannot distinguish between any cluster here. Yeah, so that is probably the dimension or the view from this perspective, or this perspective, so to say. Yeah, so if this is X and this is Y, that is the XY projection here. Yeah, and that is set here. That is the set coordinate. If we look at what is that Y set, that is this one here, then we see that we cannot distinguish between the greens and the red ones, but we can distinguish between the purple and the blue cluster. Yeah, so the 2 attributes Y set, which gives us this projection here, is the set of Y set of these 2 features is relevant in order to find the purple and the blue cluster, but not obviously in order to find the red and the green cluster. And here in that case, they are just one big soup. Yeah? And the same holds true if we look at the set X projection, which is this one here. So set in X, this set of two features is obviously super relevant to find the blue, the red and the green cluster, but not so good to find the purple and the blue one, because here in this dimension we have the big soup of those two clusters. Yeah? So you see already in a three-dimensional example, not really high dimensional, it may be that different combinations, in that case, different combinations of features are relevant for detecting different clusters. Yeah? So even if we just project on the 3 one-dimensional cases, we don't find anything, because if we just project everything on this coordinate here, everything gets one big soup. Yeah? Everything becomes one big soup. And the same holds true if we project that on this thing here. Well, we can at least distinguish between red-green and this one here, but we cannot distinguish between red and green anymore. Yeah, so we need exactly this projection here to find red and green, and we need exactly this projection here to find purple and blue, and nothing else actually. More or less nothing else. So if we go, add one more dimension like this one here, then we get again a big soup. And if we delete one of those dimensions here, we at least lose some of these patterns here. So you see that, and this is just because we have probably the different semantic layers here. We have one semantic layer which knows about a cluster of purple things and blue things and some other things. And there is a second semantic layer, semantic concept or whatever, which knows about a red cluster and a green cluster and something else here. So this is kind of baby-shaped game, now concrete in a three-dimensional feature space with red, green, and purple. And so red, green may be the clustering according to color, and purple, blue may be according to shape. And here even points are not clustered differently in different subspaces. So that's just that each point belongs probably to exactly one cluster, green. At least that is how we created, how we generated this data set. So there's not even some kind of M-to-N relationship between points and clusters and subspaces. So things can get even worse if we add a lot of more features, as you can imagine. And now it's getting even a little bit more complex, because I already told you about this thing about the concentrations of metabolites in the blood of babies. This Bavarian newborn screening data set. The task was to cluster the test persons, the babies in that case, to find groups of individuals with similar correlations now among the concentrations of metabolites. And because those similar correlations among concentrations of metabolites indicate some specific metabolic behavior, for example, some kind of metabolic disorder. So the data set probably looks like something like this. We don't know exactly because it's 40 something dimensional, so we cannot really visualize it, but probably it looks pretty much like this. So we have a healthy group of kind of noise points, and then we have some clear correlations among concentrations of metabolites, one here, in a kind of simplified two-dimensional view here, and this one here represents one specific disorder. This one here represents another specific disorder. So here now, and look, this looks a little bit different like this one here, pretty much the same, but what is the difference? Well, here the whole thing, the relevant things are axis parallel. So the projections we need to find in order to find the patterns, the projections are just projections of existing axis, axis parallel projections. Here it's completely different, because we're talking about correlations which are somehow arbitrarily oriented in the feature space. So these correlations may exhibit or may exist through subsets of features. and that makes the whole thing even a little bit more complex, even a little bit worse.